Okay, so we continue from the point where we left off in the last class. We just have a quick revision of the sessions that we have had done. And from there, what we'll do is we will have a discussion around that. So in the last class, we were talking about the different kinds of, the different aspects of probability theory. And from there, we started talking about the different kind of the distributions that come up. Now, while I talk about the distributions, right? So what I have been talking about is the probability distribution, the probability distributions the like binomial distribution. We had talked about the role of the distributions that crop up as far as, or the role of the distribution that crops up when we start working with risk models. What are the areas where risk models play an important role, where distributions play in framing the basic concepts of risk modeling. Now, having said that, the next part that we have over here is so last class we started talking about the random variables. We did talk about the concepts of continuous random variable, and we did talk about the concepts of a discrete random variable, and so on. Now, having said that, the next part that we talk about today is we will continue with the concepts of probability distributions. But today we would be extending them towards more of continuous distributions, right? So while we talk about that, before I move into this discussion, so just let me clarify one thing that can you tell me what exactly is the difference between the mathematical approach of probability and the axiomatic approach? So at a theoretical level, what is the difference between the axiomatic approach and the mathematical approach to probability theory? Okay, so what I'm saying is we had discussed different basics of the probability theory, right? So different approaches to probability theory. So now, when I try to do this, when I talk about probability theory, right? So what is exactly the advantage of uh, the numerical theory of probability over the axiomatic approach? I had identified, I had explained this difference last class as well as last to last class. So can you recollect that? Okay. So the basic difference between the axiomatic difference and the numerical and the mathematical probability of theory is as follows. The mathematical theory allows for creation of, it helps us to deal with continuous variables as well as discrete numeric variables, right? So given this given this the next part that we talk about, or the part that we have been talking about since the last class, was based on numerical probability or mathematical theory of probability, where we could understand the description of random experiments both under continuous as well as discrete random variables. So, numerical probability theory helps us to generalize the theory from a discrete to a continuous theory as well, right? So that is basically the idea. And in the last class, we started talking about, we had a discussion about the binomial distribution, right? We talked about the different, so how does the probability mass function, and how does the probability, how does that random variable, how does the probability mass function for this particular variable come into play? So that is something that we had studied in the last class. So binomial distribution, just as a refresher, let's just recollect that a binomial distribution is a distribution where you have two different kinds of outcomes to an event. Either it's a success or it's a failure, and to each success or failure there is an associated probability. And my objective is to understand that out of a given number of trials, what would be the probability of, like, out of given number of trials, what would be the, so what would be the probability that out of x number of trials there would be n number of successes? So that is, or out of n number of trials there would be some x number of successes. And in regards to that, what we have seen is that this binomial distribution plays a very important role in plays a very important role for income. It plays a very important role for risk model development, because most of the outcomes that we have in credit risk modeling are dichotomous in nature, and to each of the outcomes we either have a probability of success or a probability of failure, right? That is the reason why, most of these outcomes, also most of the joint probability distribution functions for credit risk are, they follow binomial in nature. Now, to your question, so Anirudh has a question over here. In binomial, x can be continuous or it needs to be discrete. So, binomial distribution is only a discrete distribution where the outcomes of the random experiment, where the outcomes of the trials are discrete in nature, right? So that is what the basic idea is. Now, binomial distribution is a discrete probability distribution. Clear? Since, say for example, when I'm giving out a loan, I know that the borrower can be good or the borrower can be bad. And to each of these outcomes, there is a probability. Now, what I want to know is that if I am giving out 1,000 loans, what are the respective chances of getting one bad borrower, getting two bad borrower, getting three bad borrowers, and so on. And with this, what we come down to is the probability distribution. So given this nature of the random experiment, given the nature of this values, uh, there we can model this lending procedure, or model this finding using a binomial distribution. In credit risk, binomial distribution is something which would be used very frequently. Now, okay, so over here to your question, Anirudh. So Anirudh asked me why is discrete, but X is also discrete. Now, Y is not discrete. So when you are mapping a distribution, right, your X is the outcome, and your probability value, X is the input and your probability value is the necessary outcomes, that is the necessary probability that x is equal to x. So probability that x is equal to, so this is a probability of getting one success, a probability of getting two successes. So this is a continuous value. So this is continuous. Continuous as in, since the outcome is a probability, therefore this lies between 0 and 1. So your, in your distribution, whenever you are defining a distribution, right? So what you are talking about essentially is continuous, right? Now the next part again that we need to talk about is, now the next part that we go to talk about is how would the binomial distribution actually look like. So how does binomial distribution look like? How does the binomial distribution look like? So now let us understand that what do I mean by when I say that how does a binomial distribution look like. So what I want to understand is that whether a binomial distribution is symmetric versus whether the binomial distribution is asymmetric. Is asymmetric. So this is where we want to understand the symmetricity of the distribution. So what do you think? We have discussed what binomial distribution is. So what do you think? Should a binomial distribution be symmetric or should it be asymmetric? So Kumar says, can be both symmetric and asymmetric. Why? So what are the matrices, or basis what will you say that it's symmetric and asymmetric? But yes, Kumar, you are absolutely correct when you say that it can be both symmetric and asymmetric, right? So what happens? So let's first of all let's just recap what a symmetric distribution and what an asymmetric distribution looks like. So basically, an asymmetric distribution is one which is asymmetric in nature. So over here, if your distribution is an asymmetric distribution, then you will get a graph like this. Whereas, so there would be undue concentration at either end. The next part is that when you have this, there you will have a, if you have a symmetric distribution, that is where you will have this, where your distribution will be, or your graph will be more or less similar depending on the probability concentrations. Now, let us recollect the, you know, let us recollect this. So let us recollect how the function looks like. It says p to the power of x, I mean ncx, p to the power of x into. So over here it talks about p to the power of x into q to the power of n minus x. Right? Now observe that it says, if we think about this very intuitively without getting into the mathematics, when we say that it's p to the power of x, so this p to the power of x is the probability of the success, right? Now, say suppose if p to the power of x, if p is very small, let's say that p is which is less than 0.5. So if p is less than 50%, say the probability of success is 1% or 2%. So if you think about it, what it says is that if the probability of if the probability of success in one single trial is zero point 0.5 or less, say the probability of success is 3%, right, for single trial. So it means that chances of getting high number of successes will be very low. Why? Because the probability of one single trial is very low. Therefore, what happens is that if p is less than 0.5, then we get to see that the successes tend to concentrate towards the lower end. So if the chances of uh, success of one single trial is less than 0.5, then then what we get to see is then what we get to see is the chances of getting high number of successes is very less, and the chances of getting low number of successes is very high. Right? Are we clear with this? Hey, hi guys. Yes. So is that understanding clear? That if p is less than zero point 0.5, if the probability of getting success in a single trial is very small, then chances of getting low number of successes is actually very high, and chances of getting high number of successes is actually very low. So therefore in that case the distribution will be a right skewed distribution. It will be right skewed. Now the next part that I have over here is that if p is, or if the probability of success is 50%, right, therefore it is more probable of getting mean number of successes. If p is equal to zero point 0.5, then So if P is equal to 0.5, it means that the number of successes will cluster in the central parts, right? So in that case, the your modal successes or your median successes, they will all lie towards the middle, and hence your distribution will be like symmetric. So if at p equals to 0.5, it clearly means that if the chances of getting one success is 50%, therefore the number of successes that I can get in 100 trials or 1,000 trials will circulate or will be around the middlemost values. Similarly, if p is greater than 0.5, that is the probability or the chance of success is greater than 50%, then this implies that there would be a huge probability of success, right? So in that case, chances of getting high number of successes is very high, and chances of getting low number of successes is very low, and you will have a left skewed distribution over here. So it is the probability of success of a single trial which ensures the probability values, So therefore, this is where we need to. This is how the skewness of a binomial distribution is affected by the probability of success, right? Clear up to this part? And within the domain of risk modeling, our objective will be to estimate the probability of success or the probability of failure for this one trial, right? So basically, if a model is being developed, when we are trying to develop a model, right? So I'm giving the loan to a particular borrower. So what is his chances of being a good or a bad borrower, right? And based on that, what we are trying to do is we are trying to develop the probability of default model, or with the basis that we are trying to develop the chances of the probability of a particular observation being greater than 0, zero point 0.5 or less than 0.5. Okay, so coming to this, so Anirudh has a question. Can you please explain axiomatic with an example? So axiomatic theory of probability is nothing but it is that theory which is, or it is that part of the theory which is which uses the set theory axioms to establish results of the probability theory. Say for example, I want to find out that what is the probability of event A and event B to occur together. So that is, what is the probability of A intersection B, right? So that is where we need to have this axiomatic theory. So over there, by looking into the set theory framework, what we know is the following. Say probability of A intersection B, which is equal to probability A plus probability B minus probability of A intersection, right? So the theory which establishes or which tries to establish certain results of probability theory, deriving I mean deriving them from the probability theory, deriving them from the probability from the set theory basis, those are known as the probable. I mean, those are called the like what should I say? So those are called the axiomatic theory. So the role that axiomatic theory had to play was it helped in generalizing non-mutually exclusive and independent events. Right. So previously under the classical theory, people focused only on one group of events which were mutually exclusive and equally likely. However, the events could be both mutually exclusive as well as equally unlikely, right? So in that perspective, those variables were to be like you know so basically that more general class of event where the probability was non-equally likely and non-mutually exclusive, so to take that part into account, this assumption was this band strand of theory actually came and it helped in explaining how is it that events which are non-mutually exclusive, non-equally likely outcomes are or would be like you know for them how can the probability of different kind of outcomes would be calculated. Yeah. So and but the limitation that axiomatic theory had was that they could not extend continuous events, and that was done by the numerical theory, the probability of mathematical statistics. I mean the theory of mathematical statistics. Clear? Anirudh, does that answer your question? Okay, I had explained this in the class when I did this, but I'll just come across again. Say I want to find out, sorry, this was a union intersection. Say for example, I have a box like this, A and B. Now I'll say that probability of A union B. What does A union B mean? So if I say that I'm trying to compute the probability of A union B. So what am I actually trying to do? Can any one of you write it on the chat box? Preeti, Kumar, Srinivas, anyone? What do you mean by A union B? I hope you guys are making notes as I'm going forward, right? No, it's not the joint probability per se. What type of joint? The area covered by both A and B, right? So basically, this talks about the probability of events where A or B, right? There are three groups of people, right, who would get admitted into the process. Now, so what I say that what is the probability that group A or group B gets admitted? Now, what happens over here is that if I'm saying that probability A union B, so it is nothing but, very simply, it is going to be probability A plus probability B. A plus probability B. Now, when I do this probability A plus probability B, now you would see that if I do this probability A plus the probability B, then what I'm doing is, this is A, I'm computing it once. Now this is B that I'm computing again once, right? Now you will observe that this interior portion is getting double counted. Is getting double counted. So A intersection B is counted in twice. Counted twice. Now to avoid this double counting, what we are doing is, we are removing probability A intersection. This A intersection B is double counted in this probability A plus probability B calculation. Therefore, what we do is probability A intersection. And if the two events are mutually exclusive, then this A intersection B is a big zero, because A intersection B says that A and B occurs together. Now, if we have mutually exclusive events, it means that they are totally foreclosed, right? So the chances of the outcome to occur is generally foreclosed over here. So then it becomes, the union becomes probability A plus probability. So this is how the axiomatic distribution, the axiomatic theory works. And to it, however, whatever you see is the outcomes over here are discrete outcomes. These are not continuous outcomes. So axiomatic theory cannot work with continuous outcome, and hence the generalization to mathematical theory, which helps us capture mathematical distributions very effectively. Clear? Piyush, Preeti, great, great. Okay, guys, just give me a couple of minutes. I'll just order my lunch and I'll be back. Just give me a couple of minutes. Okay. Uh, Thank you. So after this, yeah. So having now coming back to the part of mathematical probability. So when we talk about mathematical probability per se, so the most important concept as we had discussed was the concept of probability mass function, probability density function, and probability mass function was relevant for variables with the discrete outcomes, and continuous and probability density function was relevant for variables with continuous outcomes, right? So having said that, the next part that we talk about is, or the next part that we look into is uh, this. So from here we next move into talk about the next part of the the discrete distributions, and the variable which follows and the distribution which automatically follows the binomial distribution is nothing but it's the Poisson distribution. So the Poisson distribution is said to be a limiting form of the binomial distribution. And it can actually theoretically be shown that if the binomial distribution, if n tends to infinity and p tends to 0, then np will tend to lambda, right? So basically, so what exactly is Poisson distribution over here? The Poisson distribution over here is extension, this Poisson, or we say that a distribution limits to or tends to a Poisson distribution if from a binomial distribution if the following changes happen. Number one is binomial distribution is constructed for n number of finite trials. In Poisson distribution, what you have is n tends to infinity. The next part over there is that the probability of success is sufficiently large. Now, if n tends to infinity, the assumption that we have over here is that p tends to 0, right? And from there, what happens is np tends to lambda, and np tends to lambda, right? So, if these characteristics are satisfied, if these characteristics are satisfied, then what we would have over here is the Poisson distribution, and the Poisson distribution looks like this. E to the power of minus lambda into lambda to the power of x by the x factorial, right? So this is what the Poisson distribution looks like. Now, can you give me an idea as to what type of distribution, what type of events can be modeled using Poisson distribution? So what type of events are like used with Poisson distribution? Okay, measurable events. No, that is okay. I mean, all events can be measured, right? But look into these characteristics. Look into these characteristics, and from there, try to frame an idea about what type of events can be predicted using Poisson distribution. Preeti, any idea? Just look into these characteristics. So what I'm saying is that from the binomial distribution, it tends to Poisson, right? So if n tends to infinity, e tends to zero. The probability distribution tends to the Poisson distribution, right? So now the question that comes out is that how is it that this happens? Numbers is large, okay. So what numbers is large? What type of a number is large? But the no, the probability is not zero, but the probability is, I mean, it tends to zero. So what does that mean actually? Right. So rare occurrence of large possible outcomes, right? So outcomes which can, so which rarely occur. So Poisson distribution is used to model the rare outcomes. So basically outcomes where n is very large, that is the number of trials are actually very large, but the probability of the outcome to occur is actually very less. So if you want to, if you want to define a sudden crash movement or a sudden increase or a sudden decrease or stuff like that, that is where your, or a rare event or a rare movement into, or a sudden, an unexpected loss, or loss which may not have occurred in the last 1,000 years but suddenly occurs now. So these kind of movements are defined using Poisson distribution, right? So am I clear on this part? So suppose I want to model a sudden market crash. So that is where a Poisson jump process is actually used. So outputs are variables which have very rare occurrence and whose probability of success is very large is known as, or can be modeled by Poisson distribution, right? Okay, so coming down, exactly, exactly, Preeti, unexpected losses. So unexpected losses are those losses which occur at the tail end of a distribution, and mostly these expected losses are the losses which occur as expected. So they are the mean or the portfolio losses. So unexpected loss can be used or can be modeled using this distribution, right? Okay. So the next part that we start off with is as follows. So basically, Poisson distributions, the mean of the Poisson distribution is lambda, right? So NP tends to lambda is, so that means that a very low probability of success and very large number of events, they always move towards a value lambda, right? Now the next question that comes up to us over here is that how does the Poisson distribution looks like? So obviously, yes, the Poisson distribution looks very much like, Poisson distribution looks very much, it's a very skewed distribution again. It's not a symmetric distribution, but the interesting characteristic of a Poisson distribution is that its mean and variance is the same. So its mean equals to variance is equal to lambda. Clear? So n tends to infinity, p tends to 0, and p tends to lambda. Now, coming to the next part. So these are the three broad discrete distributions that we will study. So first, starting off with Bernoullian distribution. So we start off with the Bernoullian distribution. The Bernoullian distribution is nothing but it's a characteristic of a specific trial which has some probability of success and it has some probability of failure. On the other hand, the next followed by this is the binomial distribution, which has which has n number of trials, and each of the trials have success and failure. And to each of these, there is a probability of success and there is a probability of failure. So that is, and if I want to identify the probability of getting some X number of successes out of n number of trials, then that is where the Poisson distribution comes to play. The next part that we come to talk about, I mean, that is where binomial distribution comes to play. So whenever we are developing model and wherever my business problem is dichotomous in nature, what I'll do is I will model them using a binomial distribution, right? Right. So the next part that we have over here is that when the number of trials tend to infinity and the probability of getting a success becomes very less, or the chances of the event to occur it becomes very less, then where we move towards is the Poisson distribution, right? So these are, so what we clearly, or what we can say is that the Poisson distribution is a limiting form of the binomial distribution, right? Right, clear on this? Okay, so now from here we will move into the concept of continuous distributions. So what is the most basic form of a continuous distribution that we had talked about? What is the most basic form of a continuous distribution? What is the most basic type of a continuous distribution that we have? Yes, any ideas? We had discussed the most common form of a continuous distribution. So what was it? Yes, we had discussed this functional form. What was that? So does anyone remember the name rectangular distribution? So do you remember this concept of rectangular distribution that we had discussed? Anyone? Correct. So the uniform distribution happens to be a very specific case of the random of the rectangular distribution. Now, today what we'll talk about is we'll start talking about the more well distributed forms. Right. So over here, when I talk about this continuous distribution, so one of the most important, so one very important characteristic of a continuous distribution is that the outcomes are continuous. So now I cannot say that there is an outcome 1 or an outcome 2 or an outcome 3 like this. So what I'm saying is that the outcome is continuous over here. So we have a continuous set of outcomes. Right. Now, if there is this continuous outcomes, if there is this continuous outcomes, then what are the most important distributions that we have? So we have a whole set of distributions, but at this stage, we have already discussed about two of them, that's rectangular and the uniform. And over here, we'll discuss about one of them, the third and the most important part of them, that is called the normal distribution, or as we often call the Gaussian distribution. Right. So the next part is we'll talk about the concept of being or having a normal distribution. Right. So now normal distribution is perhaps the most celebrated form of continuous distribution in statistics. Right. So it is the most celebrated form of statistics, most celebrated form of distribution that we get to see in statistics. And from there our objective is to start so basically our objective over here would be to get ourselves introduced to this particular distribution. So what is normal distribution and what is so important about this distribution? The most important characteristic of a normal distribution is that the distribution is a continuous, I mean it's a symmetric distribution. Okay, so Anirudh, which example do you want? Do you want an example of a uniform distribution or the example of a normal distribution in risk? Okay, so so Anirudh, what is that example? I mean, do you want an example of the normal distribution in risk, or of the uniform distribution range? Which is the one you ask me? Okay, so first of all, it is very difficult to obtain, kind of normal distribution in the risk domain. So talking about normal distribution. Normal distribution is a very symmetric distribution that we have. Now, in risk, variable values are not very symmetric. Rather, they are very heterogeneous in nature. So when I talk about symmetricity, what I mean is symmetric behavior or homogeneous behavior of the variable. Say for a balance received receivable balances. So what exactly is a receivable balance? The balance is outstanding. Right now, a bank offers different kind of products under a major line. So under a major product line, there are multiple products, and for each product, the average receivables would be very different. So if you are actually pulling them up together, pulling up that entire categorical data into one, then you know that there is a problem with the symmetricity because a lot of heterogeneous products get attached together and hence the heterogeneity appears. So since risk data is very categorical in nature, it is very difficult to get heterogeneous behaviors, right, which are more or less symmetrically distributed. Therefore, as a part of a data science exercise, what we do is we do segmentation exercises and we create homogeneous groups of loans, and we see that the homogeneous groups of loans are mostly, uh, you know, they mostly are normally distributed across some or many of the variables. So basically, normality implies two things at a very basic level. One is the symmetricity of the distribution, and the second is that it ensures that the model that you have with us, I mean, the data that you have is more or less homogeneous in its behavior. Clear? So to understand why is this normal distribution and also let us just try and understand what exactly is normal distribution. So how does the normal distribution look like? Not only from a theoretical aspect, but also from a concept of meaning or a interpretation aspect, right? So this is what we need to do next. So starting off with normal distribution. Right. So how does a normal distribution ideally look like? So a normal distribution looks something like this. So it looks like something like this, which is very symmetric in nature. So basically, if I actually split the data into two parts, so if we actually split the data into two parts, this side, so this side of the distribution and this side of the distribution will be very different from each other, right? And hence, what we'll get to see is that and hence what we get to see is that on both sides, the left hand side and the right hand side, the values are more or less similar. So what it means is that the variable values are symmetrically distributed. So this is the very basic idea of normal distribution, and and another very important characteristic that normal distribution, or what makes normal distribution so important, is that it forms the heart of all the possible assumptions, right? So over here they form the heart of the distribution. So most of the theoretical analysis, right? So going forward, so be it the regression model, be it the logistic regression model, or be it whatever the model is, we get to see that X follows, or I mean, the theory is premised on the basis that X follows a normal distribution with given mean and variance sigma square. So the next part that we need to talk about over here is we need to understand that what exactly is this distribution, how is this distribution like, what are the advantages of using this particular distribution, why is it that most of the testing procedures, most of the theories are built up on this particular assumption. Yes, Srinivas, please tell me. Okay, so that's a good question, Srinivas. So Srinivas asked us a question that in real life scenarios, do we really use any other distributions apart from normal distribution? Yes, in real life scenarios or in modeling real time scenarios, we use all other distributions apart from normal distribution, because it is really very difficult to get variables in risk which are normally distributed, right? And hence that is where like normal distribution does not play the game. But mostly for testing procedures and all, we have to we use normal distribution, or we need to create the model segments and such like that in an order such that the assumptions of normality can be punched into it, right? Great. Okay, fine. So let's see what the normal distribution is all about, how does it look, and so on. Correct. Anirudh, when you say that the normal distribution has a PDF, it is absolutely correct, because normal distribution theoretically is based on the idea that the outcomes to be continuous in nature. Okay. Okay, great. So let's see how this normal distribution is defined generally. So normal distribution is defined by a probability density function or a PDF. So this is what is fx equal to 1 to pi sigma into e to the power of half x minus mu. X minus mu by sigma whole square. So where we say that mu is belonging to minus infinity plus infinity. So that is mu takes up all values between minus and plus infinity. The next part is x belongs to minus infinity to plus infinity. And sigma is greater than 0. Now, if you think about it, the symmetricity itself is ensured by the fact that x and mu are significantly different. I mean, it is ensured by the fact that you have a square over this. So even if x minus mu is negative, it will get squared and become positive. If x minus mu is positive, then it remains positive. So that means what I can say is that all the minus x's will have probability values which is exactly a reflection of the plus x's, right? So if x minus mu is negative, it will have the same reflection as x minus mu to be positive. Clear? So this is how this is what is the most important property that normality has, and this is called the property of symmetricity, or this is also called an even or odd function. So there is property of symmetricity. So this is called the property of symmetricity. Now let us understand that what are the most what are the most important characteristics of this distribution. So this distribution has something called an expected value of mean. So if x is a random variable, then the expectation of x over here is equal to mean. The variance of this variable x is sigma square. So over here what I have is the variance of x. So basically the normal distribution is defined by the mean value and the variation about the mean value. The variation about the mean value. Now, this is one of the most important characteristics. So that's a constant mean and there's a constant variance. Guys, just give me a moment. Okay, so as we were saying, over here, what we have is that for a normal distribution or a normal distribution is characterized by a constant mean and a constant variance. And given that it's symmetric distribution, the mean, median, and the mode come together in making. So basically, for a normal distribution, the mean is equal to median, that is equal to mode. Is equal to the mode. Right. So basically, what we'll have is, so these are some of the important characteristics that a normal distribution has. Now, what I can say is that this is a kind of a theoretical distribution which I have seen to be over here, right? So there is this distribution, and this distribution is called the normal distribution. This is called the normal distribution. Right? When you have this normal distribution, so if I split this into two parts, right? So this part is where you have your mean. So this is your mean. So mean, which is equal to mu. Then I have the median over here, is equal to. Okay, so over here, what we have is the mean to the median is equal to the mode. And where all these three descriptive measures they come together, that is where we know it that there is this symmetricity, right? So and the variance over here is this, right? So is this part understood? So the deviation about this is sigma. I mean the variance about this is sigma square. Okay, so over here what we have is So this is what the basics of normal distribution is. So normal distribution is a distribution which has constant mean, constant variance, and where the mean, median, and mode is equal. Also, the sigma square is, or the variance is less than or is lower compared to the mean. And given the fact that the variance is compared to the mean, therefore what we get to see is that there is a concentration these about the mean value, right? So all the observations are more or less clustered, symmetrically clustered near about the mean value. So with this, what makes it, and given the fact that mu is, with sigma square is less than mu, you can say that yes, this distribution is very, very, very symmetric in nature, right? So now the question that comes out is, number one, that how is it that I would know that a variable follows a normal distribution? So for doing that, we need to derive out tests of normality. We'll derive out the tests of normality. Derive out the tests for normality. How is it that we can test using the normal distribution? So how is it that we can test that whether a variable is normally distributed or not? So this is the part that we start from tomorrow, right? And in tomorrow's session, we will have a kind of we'll have from 2:30 to 5 kind of a session. Okay, so we'll have around 2.5 hours of session at a stretch in tomorrow's class. And tomorrow I'll tell you when is it that the last week's and another the last week sessions, and so I believe we have made 3 sessions till now. So how is it that we are going to make up the 3 sessions over the next 2 weeks? Right, so that is what I'll tell you tomorrow. So tomorrow I am actually going back home, and once I reach home I'll be able to plan that sessions better. So we'll do 2.5 hour session tomorrow, and next week we'll over the next 2 weeks we'll plan out the remaining, right? Thank you, and so much from my end, and let's meet tomorrow. Thank you.